Hi, I'm going to demonstrate the Dolomite droplet generation system. What we have on the bench here are two P-pumps. These are connected via a linear connector and an interface to a droplet junction chip. We also have a camera system, and we also have a compressor which is providing compressed air to the P-pumps. So this compressor is turned on at the beginning and primed, and then it doesn't need to be run during the experiment because the P-pumps don't really use up much air supply. Alternatively, if you don't want to use a compressor, you can plug in to your lab air supply, or you can use a pressurized gas bottle. So the first thing we're going to do is prime the system. So on this P-pump we have water, which you drop into the pressurized chamber. On this P-pump we have mineral oil with some surfactant in it. And what we're going to do is so essentially with the P-pump we have a dip tube. So this pipe, this is 1.6mm pipe, which we're going to push into the fitting like that, and this connects up, this tightens down. So this is our dip tube. If you come and have a look, this then dips into the vial and closes, and that's the pressurized chamber, which is used for essentially pumping the fluid into the chip. So from the front we can set the pressure, and what we can do is on the Dolomite website there's a flow resistance calculator, and essentially what we do here is if we're using a custom flow resistor kit, which we use in this case, which is using 0.1mm internal diameter pipe, we can put in the length of pipe, the ID and the pressure, and it will tell us what flow rate we'll expect to get. We also put in fluid viscosities, but some of those are listed on that calculator. So that tells you roughly what flow rate you'd expect to get using this calculator. It's basically a step-through system where you set the pipe geometry, then the pumping type, fluid viscosity, pressure, and then it gives you the answer. So what we've done here is we've worked out that for water we're going to have a pipe which is 0.1mm internal diameter and 1.5 meters long, which is our custom flow resistor. We also supply standard flow resistors, which will give a calibrated fixed flow rate. So these can also be used in place of the custom flow resistor. And again, for the oil, we have two streams coming from the oil reservoir coming to the connector. So what we're going to do first is we're going to prime these lines. So we're going to set some. So from the P-pump, I can scroll through, and I'm going to set a pressure. That clicking noise is the pump basically setting the pressure in the reservoirs. And let's see. So on the connector we can start seeing that the fluids are coming through. So I'll just adjust this slightly. So you can see you might not be able to see that very clearly, but on there the fluids are starting to come through at the tops of the pipes. So that tells us that all the pipes are fully primed. So initially, if you're starting an experiment, and all the pipes are full of air, you need to wait for what you need to apply pressure and wait for the fluid to come through. So the next step, I'm going to just vent these two reservoirs. Okay, so that's taken them back to atmospheric pressure, so there's no pumping happening now. So what, I'm going to take the chip. What we have here, it's a little bit difficult to see, but we have a droplet junction chip, and we're going to use the cross junction with the two outer streams being oil and the central stream being water. Now this chip's going to drop into this H-chip holder, and I've got another connector mounted on the other end, and this connector is going to screw in. So essentially what's happening here is we have the chip has the channels come out the edge of the chip and come in the side of the chip, and then we're connecting with the seal to the edge of the chip. So the flow's going directly from the pipe into the channel, and we're not going through a drilled fluid hole. So I'm now going to mount it mounted onto the camera system. Like so, and I'm going to turn the light source on, and we're going to have a look at the video. So, okay, so this chip, so we have used this chip previously, so it's got a bit of fluid in it. So what we're going to do first is we'll switch on the water. We turn the pressure on the water. We turn the pressures back on. So I'm going to select. Turn the pressure down. So I'm going to select a pressure of about 250. So we keep the pressures relatively low to start with, because we don't want to get any. We want to just start it off slowly, and then we can build up speed. So I'll set a pressure of 250 millibars, and this is around 140 millibars. So again, we're pressurising the two chambers. If we turn the light up a bit here. So in a minute we'll start to see the fluids coming through on the junction. So this may take a little bit of time. So we know the fluids have primed the pipes, but they're still priming the chip. Okay, so we have some air. This is air here. This is oil, and this is water. So we still have air in this channel. So if we zoom out, we can see that our oil is coming along there. So it's just taking a little bit of time. So I'll turn the oil flow rate up a fraction. So I'll turn the pressure. Just increase the pressure on the oil. You can see that's just speeding up the oil flow rate at that point. So again, here's another air bubble coming around there, and if we zoom back in, okay, so what we have now, we have the oil and the oil coming in this direction, and we have the water stream, we have droplets. We've got a few air bubbles which have been left there from the priming process. So in order to get rid of those air bubbles, I'm going to first turn up the water. I'll just increase that. Add about 50% to the flow there. And you can see instantly we've increased the water flow rate. Just increase that a fraction more. And I'll just increase the oil. Okay. So you can see we're going quite a high flow rate now. We've still got this bubble, but this bubble will clear out in a little while. You can see that. Okay, so we've got droplet generation. We can sort of get up and running fairly quickly, and you can see we can see these are very monodisperse droplets, and we can also by adjusting the flow rates, we can adjust the size of the droplets. So if I increase the oil, if I decrease the water flow rate fractionally, let's decrease a bit more than that. You can see we're starting to reduce the size of the water droplets. Now in this case, we have to be a little bit careful here. If we reduce the pressure on the water too much, then we can get a backflow scenario where the oil flows back down the water pipe. So, but you can see the droplets are reducing in size there. So what I can do, if I come and have a look at the P pump, then what I can switch from pressure control to flow control. So essentially I go to control, so it's currently, and I select flow control, yes, and then back one. So essentially what we've got on this P pump is we have a flow rate sensor. So the flow rate sensor measures the flow rate, and essentially what we can do is we can change the pressure to achieve a particular flow rate. So it's set at a flow rate of 0.77 microliters per minute. So this is unfortunately this is at the limit of the sensor. So I can try reducing that. So it will then adjust the pressure and get the flow rate down. So we have again back look at the droplets. We're again making slightly smaller droplets there. And now what I'll do is I'll change in order to get even smaller droplets, I'm going to increase the oil flow rate. So let's have to be careful to adjust this. Okay, so it's increasing the oil. Okay, it's quite nice actually that because of the frame rate of the camera, these are staying stationary. We can see we're getting a droplet. This is going to be around a 30 micron droplet, which we're generating at the moment. And these are currently coming out of the chip and being collected on this output pipe here. Okay, so if I now reduce the oil flow rate, I'm going to make a dramatic reduction in oil flow rate. I'm going to reduce it by a factor to about a quarter of the flow rate it was previously. So if we watch the screen, okay, so so it's taken the droplet size up to about 80 microns. I'll reduce a little bit more. I'll reduce it by half again. Okay, so it's about 100 micron, the droplets are about 100 microns in size now, and you can see they're starting to bunch a little bit. I'll go down again, I'll reduce oil flow rate by half again. Okay, so you can see the droplets are now increased. So the droplet size is around 150 microns. And they're starting to bunch up a little bit there in the chip. Okay, so that's droplet generation. We could leave that running because we have currently we have 2 vials. Each one's about 20 microliters per minute. We can leave that running for potentially hours on end, and it would just sit there running. We have a couple of additional modules. So, for example, if that's not enough, if 20 milliliters is not enough volume, we also have a pressurization, a reservoir which is 400 milliliters of fluid, which keep you running for sort of days or weeks on end. We also have this remote chamber. So what this allows, I'll come over here. So essentially the benefit of the remote chamber is that you can mount this on a hot plate, and then you can put your fluids in and keep them at a constant temperature. We also have here, we have a 3-way lid, so you have 3 inputs, which is quite useful. Sometimes, in this case, we've come out of the pump and we've split here, but this has some dead volume associated with this type of connector, so instead what you have is the two ports going directly into one vial. Or additionally, we have this type of adapter which drops in, and we can use a tube which drops into the chamber, and then so you can actually this allows you to pump very small volume, so you can pump like half a mil, 250 microliters of fluid. You can have three of these vials inside the pump, so you can actually pump 3 different fluids at once. So you can actually run this experiment with 1 P pump, but you can't vary the relative values of the flows. You have to keep the ratio the same and vary the whole thing up and down. But it's potentially possible to, by adjusting the flow resistors, you can adjust the flow rates ratios. So that's one quite useful. So this comes with there's a different version of the pump which doesn't have the chamber here, which plugs directly into this chamber. As I said, there's a version of this which is 400 microliters in volume. 400 milliliters in volume. We also have, for actually heating the reaction, we have this hot plate adapter which drops onto a hot plate like so, and this is a covering insulating layer. So basically what happens is the chip, so if I want to wander over in this direction, the chip, I'll just turn the light source off for a second. So we're still running droplets in this chip, so I'll just keep that in there. So basically the chip drops inside there, and the lid goes on, and then the whole droplet generation process is run at a temperature which is set by the hot plate. In addition, if you're running fast, we have these channels where you can push the tube into the channels, like so. Essentially what that does is it preheats the fluid, so when the fluid arrives at the chip, even if it's flowing quite fast, it's preheated to temperature. There's one other thing which is just trying to find. So the final thing I want to show quickly. So in addition to, I'll take this out of here again. So one of the potential issues is when you come off the chip, if you've got a good surfactant, then the droplets will go into the tube and you'll collect this up. You can see there's some emulsion being collected there. In some cases, you have, if the surfactant isn't as strong, then when you go from the chip to the tube, you sometimes get some coalescence or merging of droplets. And so we also have a version of the chip which, rather than fitting in the holder, has a header. So I'll just demonstrate this quickly. I'll just depressurize. Okay, so I just vented those. And this, essentially what we can do is essentially what happens here is the fluid, we have the same junction geometry, the channel just comes out to the edge of the chip, and you'll get a sort of bead of emulsion forming on the outside, and this can be dipped into a solution, so it can be dipped into a beaker with oil, and so the droplets break off the end. So that can be quite useful if you're trying to collect delicate droplets which have a tendency to break up. This will improve the collection potential. The other thing to mention, we also have this valve on the system. I forgot to demonstrate this, but this allows you to switch the flow on and off. So this can be quite useful. Essentially, with pressure-driven flow, you can just switch the flow rate. You can just use this valve and just stop the flow rate instantaneously. So it's quite useful for controlling. As I say, the main benefits of this type of system over a syringe pump system is, as you will see, is you can have very fast response to changing the flow conditions. Whereas with a syringe pump, you make a change to the flow rate, and quite often it takes a while for the system to expand and achieve the flow rate which you need. The other thing is also, the other thing is you can also we can also use stirrer bars, magnetic stirrer bars. Obviously, we can use those. They work fine with this remote chamber, but they also work. They also work with the P-pump, so you can actually put the whole P-pump on a magnetic stirrer, and that works fine. The other thing is, as I say, the flow sensor can detach. The flow sensor plugs into the back of the P-pump. In this case, we also have there's also this version of the flow rate sensor which has a display on it. Again, this can plug into a P-pump, or it can plug directly into your PC. As is the case with this sensor, it can plug into your PC, so you can just monitor flow rate independently of the P-pump if you just want to use it as a flow sensor. And this part, this it breaks into two parts. This is the interface, and click on that. And this is the sensor. So the sensor, there's a range of different sensors. This one gives you a flow rate of 1 microliter to 50 microliters per minute, which is a good general flow sensor for this type of chip. But there's other ones which have smaller flow rates and larger flow rate ranges. And that just clips into your pump. The other, so that's pretty much covers everything there. There's one other, the only other type of droplets, there's one other type of droplet chip. So we have so this is a small droplet chip. So these smaller droplet chips are for running droplets in the range, so going below 30 microns down to about 2 microns. So this chip has, rather than having holes coming in the side, because the channels are quite a lot smaller, we have to use the top-down holes. So this chip actually has channels which are about 5 microns deep, but there's also a version which is about 14 microns deep. So this chip goes into a top-down interface. I think it's slightly damaged. So I can just demonstrate. So it's set up pretty much the same way. So the linear connector screws in like so, and then you just post the chip in. like that. So essentially you have the oil and the water in the same positions. The channels are smaller, so sometimes you have to put slightly higher flow resistors on because it's lower flow rates. And then on here, it clips on like that, and it's illuminated. I don't know if we can see. Okay, I think I've lost the screen there. But anyway, this allows you to illuminate the chip, and this microscope, you can sort of see droplets down to around the sort of 5 micron mark. You potentially need a slightly higher power microscope when you're going down to about 2 micron droplets. And this is, as I mentioned, this is a standard camera which we sell, which can get frame rates up to about 1,000 frames per second. So you can see droplet generation up in the sort of 500 droplets per second sort of range. And potentially, if you reduce the size of the picture you're taking, then you can get higher frame rates. Okay, so that's the system, and there we go.